Okay, let me welcome you everyone after the lunch break. Our next speaker will be Brandt Bucher, and he will be talking about building a just-in-time compiler in CPython. Let's welcome him with a round of applause.
Hello, everybody. So, as I was just introduced, my name is Brandt Bucher, and today we are going to be talking about CPython's new experimental JIT compiler. Before we get started, a little bit about me. I started using Python about 7 years ago, and everything since then has kind of been a whirlwind. Since then, I've contributed code to CPython by finding and fixing my first bug. I joined Python's triage team, and then during the pandemic, after working on pattern matching, I became a Python core developer. I currently work on Microsoft's faster CPython team. It's my literal dream job, and basically our entire goal is to make Python faster for everyone in this room. And we've succeeded. In 2022, we made Python 3.11 25% faster for most workloads, and we're still working hard. Specifically, last year, I personally worked on implementing CPython's new experimental JIT compiler, which is what I'm going to talk about here today. So before we get started, a little bit of background, because I think it's important to understand why we felt that CPython needed a JIT compiler now and sort of the steps that it took to get here. So a little bit of recent history. As I said, in CPython 3.11, we introduced our new specializing adaptive interpreter. And this delivered a performance improvement, yes, but the way it did it is actually more interesting. I gave a talk on the specializing interpreter last year at PyCon, but briefly, it sort of listens to your program as it runs and type specializes the bytecode and caches important values as it's running. And so while, yeah, it delivers a performance improvement, if you read between the lines, you'll see that actually we're collecting a lot of valuable data about your program in the interpreter while it runs. The exact sort of data that we would care about if we wanted to, like, I don't know, compile it later. So that's things like types, where your program is spending its time, what sort of branches it's taking, things like that. In CPython 3.12, as maintainers, we got a quality of life improvement. The specializing adaptive interpreter actually introduced a moderate amount of complexity to an otherwise pretty simple interpreter. And so in 3.12, we actually took some time to build infrastructure to automatically generate the interpreter from a DSL spec. So this domain-specific language allowed us to avoid a lot of the kind of repetitive and tedious and error-prone boilerplate that you have in the main interpreter loop. So things like ref counts, error handling, stack manipulations, and things like that. But another nice thing that kind of fell out of this is that we now have automated infrastructure for basically analyzing different bytecode instructions and generating, yeah, one interpreter, but potentially multiple interpreters, or even things that aren't interpreters from this same specification. And there's one source of truth that there's no need to keep everything in sync. And finally, in CPython 3.13, which was just feature frozen and is due out in like September, October, I think, we introduced a new micro-op interpreter. So this is an entirely separate execution pipeline that basically detects hot code paths through your code, and then it lowers them to a new bytecode format that we call micro-ops. It optimizes these micro-ops and executes them in another dedicated interpreter. And again, this is only possible because of the steps that we took in 3.11 and 3.12 to collect this interesting profiling information and then actually be able to generate another interpreter and automate so much of this translation pipeline. So I know that this is a lot, but like I think that walking through an example together is probably the easiest way to understand how this works. So I have my Fibonacci function here. It's an iterative Fibonacci function, and we're going to mainly focus on where it spends most of its time because that's where the interpreter is going to focus too. So we have this inner for loop here that basically just loops over a range and does some integer addition. I'm going to show the bytecode for this for loop here in the center of the slide. And as many of us know, CPython uses a stack-based virtual machine, so I'm going to show the stack here on the far right. Now, it's not necessary for you to understand how any of this works, but I think it's super interesting, and I think it explains sort of like why we have the JIT now and how exactly it fits into the rest of the system. So when we begin entering this for loop, we already have an iterator on the stack. So this is the range iterator that we're actually pulling items out of. And we start by executing the for-iter instruction, which is responsible for advancing the iterator and pushing the result to the stack. Now, this is where specialized bytecode comes in, because an operation like iterating over an iterator is actually surprisingly complex. It's a very generic mechanism that's inherent to Python's object model. However, there are lots of things you can iterate over that are actually very, very simple. So in the case of a range, we actually don't need to jump through all those hoops to do iteration the way Python should do iteration. This is common enough that if we can detect that someone's iterating over a range object, we can instead just create the integers directly in the interpreter itself. And so this for-iter instruction, instead of being the generic case, will quickly specialize itself and replace itself with a for-iter range instruction, which contains a fast path just for this common case. After that, the store fast instruction will store that item on the top of the stack and put it into a local variable. And then the next two instructions load three additional local variables, B, A, and B again. We're now inside of the loop. At this point, we're at the binary op instruction, which is responsible for popping both of those items off of the stack, adding them together. Again, this is a surprisingly generic operation. Think of all the different things that you can add together in Python and all the things that adding can do. Like, you can make a class that when you add, it formats your hard drive. It's a very it's a very overpowered mechanism, especially when you're just adding two integers together. And so, similar to the for-iter, we will actually specialize this generic instruction into one that's specialized for adding two integers. And this is about as fast as you can add two integers while still working with Python objects. And then after that, everything else is pretty simple. We store the two results in local variables, and then we're going back through the loop again. So you'll see that after we've actually completed this specialization stage, we actually have some decent profiling information about your program. While the original bytecode instructions didn't really tell us much, this tells us a lot about what sort of values that we're seeing, what sort of types that we're seeing, and what sort of code is actually being executed. And so this is where the micro-op traces come in. Basically, our goal with the micro-op traces is to take these specialized bytecodes and break them up into smaller, more easily optimizable parts. So we're going to do that. Once your loop has warmed up, for some definition of warm, we basically take these instructions and we start translating them automatically into smaller parts, like I said. Now, this translation step is actually automatic. Because we have our cool DSL in the interpreter generator, we can actually just define each of the larger instructions as their component micro-ops. And so this isn't a step that needs to be handwritten. It's really just a table lookup. And so once this has been done, this is where we can actually start optimizing these micro-op traces. As a first example, you can see that we have these check validity and set IP instructions at the beginning of every single instruction boundary. Now, this is something that's necessary in order for correctness in most cases. It guards against when we might escape from our micro-op trace into just arbitrary Python code. For example, if we make a call to a function or there's a callback or something. And so we basically need to make sure that the world hasn't changed too drastically, because user code can do all sorts of crazy things. It can raise exceptions, yeah, but it can also start a debugger and start changing local variables. It could even modify the built-ins and start monkey patching stuff all over the place. So this is important to have, but actually in this case, we don't really need it. Remember, we have this type information, and we know that we are actually just advancing a range iterator and adding some integers together, which there's no chance that that could invoke user code. And so we can actually remove all of those because they're pure overhead that can be eliminated entirely. Similarly, you'll notice that we have this itercheck range instruction at the very beginning of our trace that executes once per loop. This is a guard to make sure that the specialized iter next range instruction to later makes sure that the thing we're iterating over is still a range, because that wouldn't be a correct optimization if for some reason we were now in a list or something. But again, in this specific case, you can see that once we've entered this loop, it is impossible for this to be anything other than a range iterator, and the optimizer can remove it. Similarly, we have one other guard in this trace, the guard both int. This is similar to the itercheck range instruction in that it checks that both the things we're adding together are integers, and it will de-optimize if they're not. But again, like there's no chance that these are anything other than integers. They were integers when we entered the loop, and we're only adding integers to them. So we can remove that too. And again, because all of this micro-op infrastructure is built on like this generated interpreter infrastructure, we can like automatically generate lots of these passes. So I won't go too deep into it here. This is about how much I'll get into the optimization, but Ken, Jin, and Jules are actually giving a talk in this room immediately after if you want to learn more about how we're optimizing this stuff. So you just don't even need to like do anything to then watch their talk after mine. They flew all the way from Singapore, and they really want to share this stuff with you. And they're also having a portion of their talk where they talk about contributing to Python as college students. So once we have this optimized micro-op trace, you can see that this is basically the bare minimum amount of work necessary to faithfully execute the Python semantics for this for loop. We've removed all sources of unnecessary overhead, and it's actually entirely statically typed. There's no dynamic stuff left here, which is perfect if we want to like further lower it. And that further lowering is actually surprisingly necessary. Despite the fact that they're called micro-ops, the micro-op instruction format is actually quite a bit more complex than the base bytecode instruction format. It has a lot of information of like cached values and like de-optimization information and things like that, because it is kind of operating in a more constrained scenario. So decoding each of these individual instructions in the micro-op interpreter is a lot more expensive. Also, you'll notice that even though we've optimized this and each instruction itself is doing less work, we still have more instructions, so that dispatch overhead is increased, even though we've actually reduced the amount of work we're really doing. And so just by turning on the micro-op translation, optimizing stuff, and then actually running it in the tier 2 interpreter, or sorry, the micro-op interpreter, this is actually about 20% slower than just if you had done nothing at all, which is super disappointing, right? Because we just put a ton of work into making this happen. So that's where just-in-time compilation comes in. It's basically we're basically hoping that we can overcome that additional interpretive overhead and even gain back some additional performance using this technique. Specifically, we want to reduce the interpretive overhead that we've introduced by compiling these optimized traces directly to machine code. And we hope that this can help us reduce indirection in a couple different ways. The first is that we can burn in constants, caches, and arguments. So rather than having to decode individual instructions in the interpreter, we can like immediately encode those values directly into the machine code. In a similar vein, we can also move data off of frames and into registers. So you saw how I was constantly pushing and popping things off of the stack when I was in my for loop. That's basically how Python operates, is by constantly pushing and popping. However, Python frame objects actually live out in heap memory. So every time we push something to the stack, we are sending data to memory. And every time that we are popping something off the stack, or even just reading the value, we now need to read from memory. It would be much better if we could actually move that stack into registers where they're immediately available and there's no latency there. And finally, we want to bring the hot code paths inline. So the idea here is that rather than having a generic interpreter that needs to handle every possible micro-op, what we want to do is we want to create a straight line sequence of the exact code that we need to execute to reduce that dispatch overhead. And one thing that's important is that we need to weigh this against like our deployment goals. So like Python is a very widely used project with some kind of unique constraints. So for example, we need to have broad platform support. Python runs lots of places, and I would consider it not a success if we wrote a JIT and it works great, but it only works on 1 or 2 operating systems, or only on 1 architecture. I think that really, if we want to do this right, it needs to work in lots of places. Sorry, broad platform support. Another thing, too, is that I want to make sure that this thing has few runtime dependencies. Similar to the platform story, Python is used in lots of really interesting places, and it's not realistic for everyone to install a full compiler toolchain, for example, or even a C compiler at all. And so it would be great if the story were the same as today, where you could just download Python from python.org and everything just works. And finally, and most important to me, I value low implementation complexity. So Python is maintained almost exclusively by volunteer effort. And I don't think it would be successful if our new JIT compiler was so big and so complex that nobody could reason about it, no one could maintain it, no one could fix bugs in it or improve it or extend upon it. We are actually willing to sacrifice that peak performance in order to make sure that the project remains healthy in the long run and that this is something that will scale forward into the future. And so one thing that you'll notice is these goals are absolutely in conflict with one another. We want to make our code faster, but JIT compilers are historically very, very complex things. And so that comes up against our deployment goals of being able to work lots of places with very few dependencies and way low implementation complexity. And so the good news is that there's this thing called copy and patch, and it solves a lot of these problems in a very satisfying way. It's a technique for generating template JIT compilers, and it's really, really cool. So there was this paper floating around a couple of the core devs in 2021, 2022-ish. It comes out of Stanford, and it lays out this technique in a 30-page paper. I really like the paper, but if reading white papers isn't your thing, there's also a really good blog post by the same author of the paper where he's basically implementing a Lua JIT from scratch using this copy and patch technique. It's really well written. If you don't know how JIT compilers work and you read that blog post, you'll know how JIT compilers work. But basically, in a nutshell, it's a way of automatically turning a C interpreter, hey, we have one of those, into a fast template JIT compiler, which is exactly what we want. So to kind of get an idea of how copy and patch works, just as a thought experiment, if you had a sequence of bytecode instructions and you wanted to translate them into fast machine code as quickly as possible, how do you think you would go about doing that? It might look something like this. You might say, for each bytecode instruction, whoops, I missed a slide. For copy and patch code generation, we actually get pretty good performance out of this. This is from the paper. Compared to a WebAssembly baseline compiler, in this case liftoff, the copy and patch implementation in the paper gets 5 times faster code generation and 50% faster code. So we're not only generating faster code, we're generating code faster. So it's strictly a win in this case. Similarly, compared to a traditional JIT toolchain like you would see in some JIT implementations, say LLVM with a low optimization level, it's 100 times faster code generation and still about 15% faster code overall. So it's still strictly a win in this case. And as sort of like an upper bound on the sort of performance improvements that we can expect to see, compared to a handwritten assembly JIT, in this case Lua JIT, a copy and patch Lua implementation is still faster on some benchmarks, and it's only 35% slower overall. So this is exactly what I was talking about when I mentioned trading peak performance in exchange for implementation simplicity. And so, back to where I was before. If you were to compile some bytecode instructions to machine code as quickly as possible, what you might do is you might say, well, at runtime, let's walk over that sequence of bytecode instructions, and then for each one, let's copy some static precompiled machine code into executable memory, and then walk over it and fix up anything that needs to be patched up. So these would be things like jump targets or cached values, things like that. If you look at these 2 steps, you'll notice this looks a lot like something that we already have and we've had for a very long time, which are relocatable object files. So I could just as easily say, when linking or loading an ELF file, copy some static precompiled machine code into executable memory, and then patch up the instructions that need to have runtime data encoded in them. So these would be things like relocation records for extern symbols. And so this is exactly how copy and patch works. And I'm going to kind of walk through an example of how we get from this load fast micro-op into the actual code that we would JIT at runtime every time we see one of these. So this is the load fast micro-op. It's pretty straightforward. Basically, we get the value that we want to load off of the locals of the frame, we increment its reference count, and then we push it to the stack. And that's basically it. So what we want to do is at build time, when we are building the Python interpreter itself, What we're going to do is we are going to extract the body of this instruction, which is easy to do because we're generating the thing anyways. And we're going to put it inside of its own function so that we can compile it in isolation without the rest of the interpreter. And when we do that, you'll notice that right away this thing won't compile because, for example, we're accessing the frame object and we clearly don't have a frame. We haven't even begun executing yet. Since this is a function, though, we can just pass that in as an argument, and that works. Similarly, every time we access the stack pointer, this isn't something that we know statically, so that needs to be passed in as an argument too. Now, when we get to the op-arg, which is the other kind of undefined local here in this function, something interesting happens. Although this will be different every time that we JIT the load fast instruction, once it's JITted, it's going to be the same value. So ideally, we would like to encode the op-arg directly in the compiled machine code. We don't really know how to do that yet, so let's just imagine we had some like magical thing that can magically insert the op-arg at that point, and we'll leave it at that for now. Similarly, I'm guessing that we're going to be JITting more than just a single load fast micro-op, so we also need a way of transferring control flow to the next instruction once we're done. This would be the next instruction in the trace that we're JITting. And so in this case, we can also just kind of hand wave it away and say, okay, let's just magically run the next micro-op, and we'll pass the frame and the stack pointer through. And then we'll return the value from that function. Now, copy and patch gives us a really elegant solution for how to handle these two sort of placeholders, and that's by using externs. If you're not familiar with C, an extern is basically like an import in Python. It's something that you don't define, but you trust someone else to define for you at runtime. And in C, what this actually looks like is it will actually leave holes in the generated code and then tell what's intended to be the linker or loader, but is really going to be us, exactly where and how to patch those values. So when we actually compile this thing with Clang, and we can compile it with a high optimization level, because we're at build time, we don't actually care about compile time, we can get the following ELF file. And this has everything that we need already in it. On the left here, you can see that we have the raw bytes of the machine code to execute this load fast instruction. And down here at the bottom, we have the relocation records that tell us exactly where and how we want to patch those values. In this case, the op-arg and the address of the next thing that we want to run. And so this is great, but we actually have an opportunity, if we're comfortable with it, to perform some localized optimizations, since we have a very, very extraordinary knowledge of context at this point. So for example, the load of the op-arg has a layer of indirection that isn't actually necessary, because we know, based on our instruction format, that the op-arg can never be more than 32 bits. So we can rewrite this move instruction into a more efficient move immediate value. Similarly, the jump to the next instruction at the very end is an indirect jump that, again, isn't very efficient and actually isn't necessary. Since we're going to be emitting the bytes of the machine code one after the other, we can just trust that we are going to fall through into the next instruction. So this would be a zero-length jump anyways, and we can just wipe it out. Once we've done this, this is basically the essence of a load-fast micro-op. We can parse this out of the ELF file and put it directly into generated code in a C header file. And so what we have here is a function that we can call, and it will JIT a load-fast instruction for us. These are the bytes that it will copy, and then this is the hole that it will patch. And this is super fast. It actually takes almost twice as long to allocate the memory as it does to JIT the memory. And that's not because allocation is slow, that's because copy and patch is so fast. So, sort of some context on how this fits into CPython. At build time, the copy and patch implementation that's currently in 3.13 has about 1,000 lines of complex Python and about 100 lines of complex C. And this is all build time code. So this is everything that's responsible for basically compiling all of these C templates, parsing out the ELF files, fixing up some individual instructions, and then actually writing out that generated code. And we do have an LLVM dependency, but again, this is a runtime dependency. So this isn't something end users need to install. This is something that if you want to build the JIT, which it is optional, the person who's actually like compiling the Python executable itself needs to have nearby, which is much less of a heavy lift, because if you're compiling CPython, you probably have access or knowledge necessary to build LLVM or download a compiled binary of LLVM. Compare this to the runtime the runtime code, which is actually just about 400 lines of simple-ish C. But really, the core of the copy and patch JIT is one loop where we're basically just looping over the micro-op trace and calling these emit functions for every single one of the inner instructions. There's also those 9,000 lines of very, very simple generated C, and it's truly just as simple as what I showed you on the previous slide. And most importantly, no runtime dependencies. Everything is fully self-contained, and users don't need to install anything. So since we are using LLVM for this, we have incredible platform support right out of the box. In addition to supporting x86-64 on all the most popular operating systems, we also support 32-bit Windows and ARM64 on all those same operating systems with like very, very little additional effort. This is great. Like, the fact that we can just support all of this right now is like mind-blowing to me. I don't know. In terms of performance, because I know that's why you're all here, as I mentioned before, when you turn on the micro-op interpreter, it's about 20% slower. And so this isn't with the JIT, this is just with the interpreter. And we still want the interpreter around. It's useful for us to debug, because debugging interpreted code is a lot nicer than debugging JITted code. It also uses about 1% more memory, because those micro-op traces are things that are in memory. Now, our goal with the JIT for 3.13 was to get something working and to get it in so people could play around with deploying it, building it, and we could shake out any remaining bugs and just get something that doesn't crash and doesn't perform horribly, basically. And so the JIT in 3.13, if you choose to build it, again, it is experimental, it actually overcomes that entire 20% slowdown. And again, we are not actually doing many of the optimizations that I've explained to you on the previous slides yet. So this is sort of just like our baseline, and we can spend the 3.14 cycle actually improving upon this, and I'm confident that we'll be able to. Currently, it uses about 10% more memory. That's sort of an upper bound because it's based on benchmarks that have a high ratio of code to data. So typically, if you are worried about your memory usage, you probably have large data, and you won't be actually JITting code that's proportional to that. But this is mostly because we haven't really been paying attention to memory usage. And so I think of this as like a high watermark that will come down with time. And we actually do have a few external contributors who are stepping up and helping us out, get this number down. If you are curious to learn more, again, I mentioned that I gave a talk last year at PyCon about the specializing adaptive interpreter. If you're more of a reader, PEP 6059 by Mark Shannon is where you can learn more about that. I also recently wrote a PEP 744 called JIT compilation. It covers a lot of the same stuff that I talked about today, but goes into more detail on like the design decisions that we made and some of the more relevant background and sort of future plans and things like that. If you actually want to build this for yourself, it's not that hard. So if you are on Windows, you're typically using the PC build directory to do your thing. All you need to do is add the experimental JIT flag to your build, and the JIT will be built automatically. Similarly, if you are on any other platform, you can add the enable experimental JIT flag. And this works with cross-compiles and everything. So if you experience any issues, please just file an issue on CPython itself, since this is living there now. And you will need to have LLVM 18 installed, but it's actually pretty easy to install if you don't have it already, and there are installation instructions inside the CPython repository itself that give basically one-liners of how to do that. And that's pretty much it. Thank you very much. My name is Brandt Bucher. I'm at Brandt Bucher on GitHub. You can also email me at brandt@python.org. I'm not going to be doing Q&A, but I'll be right outside those doors in a couple seconds if anyone wants to chat or ask any questions. Thank you.